Chapter 7, Section 3, we are going to be talking about exponential functions and logarithmic functions, and we're going to talk about how those are connected and how you can convert from one form to the next, and then we'll also be writing, evaluating, and graphing logarithmic functions. In the previous lesson, we talked about inverses. In this example, a principal and two assistant principals are calling teachers. So in each round, so we started with 3 people, and in each round of calls, 2 or more are called. And that's an exponential function. The question is, after how many rounds are all 300 teachers called? And in order to solve this, we have to solve the above equation for x. And that is something that we haven't talked about, and we use logarithms to solve for that variable x. So it says right here, the inverse operation of taking something to the x power is a logarithm. All right, and another key statement here is a logarithm is the exponent to which a specified base is raised to obtain a given value. So we are going to use this definition to solve for exponents. At the bottom of the page, it shows you how these two, an exponential expression and a logarithmic expression, it shows how they are connected. So in this expression, we have b as the base, x as the exponent, and we have a as the answer. When we switch to logarithm form, we have log, which stands for logarithm. The base is the number, the small subscript written below log, and then you have a as the answer, and then it's going to equal the exponent. So let's think about what I just wrote. We have this entire expression right here set equal to x. And if we look at the previous equation, x is the exponent. That means the entire expression that I circled in green, that entire thing is the exponent. So like I said previously, we use logarithms to solve for the exponent. So the entire expression is an exponent. That's a concept that will help us as we move through the rest of this chapter. And I will fill this in right now. We will rewrite it in terms of a logarithm. So we're going to go log. All right, the subscript is the base, and in this case the base is 3. All right, when I simplify 3 to the 5th power, I get 243. And all of this equals the exponent. And the exponent was 5. So now we're going to get comfortable switching back and forth between the two forms. We're going to take the exponential equation and write it in logarithmic form. So we have the logarithm, and the base here is going to be 5. The answer is 25, and then the exponent is 2. So again, we have log, and the base is 10, and when we have a base 10, we're not going to actually write it. So if you have a log and there's no base written, we assume it's 10. That's a commonly used log. So the answer here is 10,000. And then the exponent is 4. The next one we have log again. The base here is 3. The answer is 1/3, and the exponent is -1. So the last one has just variables. but it's still going to be the same. Log, the base is A, the answer is D, and it equals the exponent, which is C. So looking at the first one, another way to look at this is, since 5 is the base, what exponent would you have to raise 5 to get to 25? And that would be 2. So 5 raised to the second power is 25. So 2, 4, -1, and C. Those are all the exponents, and they came from 2, 4, -1, and C. So we set the logarithmic expression equal to the exponent. Example B, you guys can try this on your own, so pause the video here, write down these 3 answers, and when you've got them you can restart the video and see how you did on this specific example. Here are the answers, see how you did. Now we're just going to go the other way. We're going to start with a logarithmic expression and we're going to rewrite it as an exponential equation. So if you know what each of the pieces means, this should be pretty easy. The first one, we have a base of 9. We have an exponent of 1, and the answer is 9. The next one, we have log base 2. So our answer is 2. The exponent is 9, so 2 to the 9th power is, the answer is 512. The next one we have log base 8, so the base is 8. The exponent is 1/3, so now we're looking at the third root of 8, and the third root of 8 is 2. Log base 2. The exponent is -2. 2 raised to the -2nd power means we're dividing 2 times, and that's going to be 1/4. The last one, log base b. The exponent is 0, and anything raised to the 0 power is 1. Here are 3 you can try on your own. So go ahead and pause the video, try these 3. Once you get them done, you can restart the video and see how you did. So we had 10 to the first power is 10, 12 to the second power is 144, 1/2 to the -3rd power is 8. 1/2 to the -3rd power means we're dividing 1/2 3 times. When you divide a fraction, you flip it and multiply. So when we flip the 1/2, it's 2. 2 to the 3rd power is 8. So I've already mentioned this. We didn't define it yet, but here it is as a definition. A logarithm with base 10 is called a common logarithm. And when we use a common logarithm, we don't always write the base. So if I had log, and I didn't write a base, and I said that the answer was, right, this assumes the base is 10. So log base 10 of 1,000, 10 raised to what power is 1,000? 10 raised to the 3rd power is 1,000. And that goes on to what we're going to be doing next. We're going to be evaluating logarithms. So A up here says 5 raised to what power is 5? That'll be 5 to the 1st power. And B says, what would I have to raise 5 to get to the answer of 1? And that would be 0. Anything to the 0 power is 1. And you can see that's also in the chart up here at the top left. Example 3, evaluating logarithms using mental math. So this is going to be depending on how well you understand what we're trying to do here. If you know what the base is, then we're asking what would you have to raise that base to get to the answer. So the first one, the base is 10. And 10 raised to what power is going to be 0.01. So we're looking for the exponent. And in this case, if you don't know what 10 raised to what the power is, you might want to convert 0.01 to a fraction. That would be and you can see that's the 10th place, that's the 100th place. That's how I knew to write it as 1 over 100. So 10 raised to what power is 100? That would be 2, but since it's a fraction, it means we're dividing 10 twice. So this one is -2. So -2 is your answer there. The next one says 5 raised to what power is 125? And you might know that 5 to the third power is 125, so your answer here is 3. And if you need to write it like this to help you figure that out, we're looking for the exponent. The next one, what would I have to raise 5 to get to the 1/5? So 5 is your base, and then in your answer right here, you are dividing 5 one time. So that means it's going to be -1 as the answer. The next one is 10 raised to what power is 0.00001. So you can see here we are dividing 10 5 times, and I got that from the number of zeros down here. So our answer here is -5. The last one is 25 raised to what power is going to be 0.04. So I'm going to convert 0.04 to a fraction. And I get 1 over 25. So this says I'm dividing 25 one time, and that is written by -1. So on a lot of these problems I wrote my work, and I'm just writing that work because that's how I'm doing them mentally. I'm looking at it in terms of this entire thing is an exponent. So 5 raised to the third power is 125. So the entire expression log base 5 of 125 can be simplified to be 3. Those are equivalent statements. Y equals 2x is an exponential function, and you can see the exponential function is graphed right there. And the inverse of that is this logarithmic function right here, and that's graphed right down there. And so by definition, inverse functions can be reflected across the line y equals x right there. So if we know how to graph an exponential function, we can switch the x and y points and graph the logarithmic function. You can see we have domain is all real numbers for an exponential function. So when we flip that, that means the range of a logarithmic function is all real numbers. The range of a exponential function is y is greater than or equal to 0. So when we flip that, the domain becomes x is greater than or equal to 0. And excuse me, it's not equal to, it's just greater than. Y is greater than 0, x is greater than 0. Okay, example 4, graphing logarithmic functions. So if we know, if we have y equals 3 to the x, we can put that in our y equals and use the table feature on a calculator. That means that 3 raised to the negative 2 is 1/9. 3 raised to the negative 1 is 1/3. 3 raised to the first is 3. 3 raised to the second is 9. 3 raised to the third is 27. Now to graph the logarithmic function, we're going to switch these values. That means that the x value is 1/9 and the y value is negative 2. The x value is 1/3 and the y value is negative 1. And that just continues on. We switch the x and y points. Now we can graph this. When x is negative 2, y is 1/3, so that's going to be a really small point. Negative 1, 1/3 is a little higher. 1 is 3. 2 is 9, and then the next point's off the graph. So there's our exponential function, and now we graph the inverse. So I'm going to go out here, this last point, it won't fit on the graph, so I'm not going to graph that one. But when x is 9, y is 2. When x is 3, y is 1. Then when x is 1/3, it's negative 1. And then when it's 1/9, it's negative 2. So it's going to go about like that right there. You can see those do look like inverses. Called it from the previous page, the domain is all real numbers for the exponential function, which means the range will be all real numbers for the logarithmic functions. The range of the exponential function was y is greater than 0, which means the domain will be x is greater than 0, and that was from the previous page. So common questions are, where did these points come from? And again, we put them in our y equals. I put the y equals 3 raised to the x in the graphing feature, and then I went to the table to fill out the values. I then changed my decimals to fractions here. That was this one was 0.3333, converted to a fraction, it's 1/3. The last example we're going to do here is simplifying a logarithmic expression. So in this particular example, we're looking for the pH. Those of you who have had chemistry know that that refers to how acidic something is. And if you look at milk, tomatoes, and lemon juice, the milk is going to be less acidic than the other two. But you can figure out what the pH value is by substituting these numbers in for the H plus right here. And then you can go to your calculator and you can simplify that. So for tomatoes, well, actually we'll start with milks. For milk, we're going to take negative log, and then we're going to put in 0.000, looks like there's 3 more zeros there, 25. Put that in our calculator, and we'll find out the pH of milk. Okay, so after typing that in, I got a pH of 6.6. Now, if you're looking for the log button on your calculator, it's on the left-hand column. On my calculator, it's next to the 7. So on the left-hand column of buttons next to the 7, you can go ahead and find out the pH of tomatoes and the pH of lemon juice. So pause it, figure those out, and then come back and check to see if they match my answers. Okay, so I got 4.5 for the pH of tomatoes and 2.2 for the pH of lemon juice. And those of you who had chemistry, this should make sense because lemons lemons are more acidic than tomatoes, and tomatoes are more acidic than milk. Okay, that's it for lesson 7.3.